Okay, let's have a look on pressure distributions and formulas, on forces. I showed you something about fluid properties, I've shown you something about forces, pressures, densities, the Archimedes principle should be known. And now we want to go a bit deeper into hydrostatics. We want to have a look how a fluid will act on a surface and how we generate forces inside the surface or inside the walls. Okay, and okay, maybe one thing I want to explain you, if we have a pressure in a fluid and the fluid acts on a surface, yeah, we will have a pressure on a surface, and maybe you know what this in what the result will be inside the solid. We will have stresses and tensions inside the walls now. If we have a wall, we have a fluid, we have a high pressure inside the fluid, the pressure acts on our wall, on our surface, then we will have stresses inside the wall. And what happens if stresses are too high? The wall will be damaged. For example, imagine you have a dam. You have a dam here, you have a water pond and a dam inside the water, and to generate some electricity. And if the water is too high or too much water, too heavy, the dam will break, the wall will break. And this happens always if the stresses inside the walls are too high and higher than the material can handle it. Okay, so here we have our pond, we have our water pond, we have our fluid, we have a density of the fluid, and please always remember, water has a density of 1000 kilograms per cubic meter. And then we have, if we go deeper and deeper into the water, the pressure will get higher and higher. Yeah, because we calculate the pressure here with this formula. We calculate with density of the fluid times gravity constant times deep in the water. So if we come deeper and deeper, pressure will be higher and higher. And so at the bottom of our wall, of our dam wall, we will have the highest forces. And maybe if you sometimes have a look at a Dutch dam system, maybe I can also, in the next slide, I can look for some photos. You will see the wall at the bottom of a dam is always has the highest thickness because there are the highest forces. Okay, and there's also another thing. If you make this calculation of the forces inside the fluid, you must always add the forces, the pressures that are over the fluid. Yeah, here if you have over the fluid element a high air pressure, you must add it. Yeah, 1 bar. If we now here on Earth we have about 1 bar, but 1 bar is still a lot. Yeah. Okay. So I always like to introduce some famous scientists that have invented a lot of formulas that have helped us a lot in fluid dynamics. And one famous person that made a lot of inventions in fluid dynamics, and he made a lot of fluid dynamic calculations, was Mr. Euler. And he invented the basic law of fluid dynamics. It is named after him, and it is the balance of volume force and surface force. Yeah, if you have a volume, you have a pressure inside, you have a force inside, then you get also force on the walls. Yeah? So Mr. Euler, he lived in the 17th, 18th century. Yeah? Okay. So, and please look into some earlier lectures from me about the meaning of the Nabla operator. I have already explained this in an earlier lecture. Okay, here is it again, the Nabla operator. What is this? Is the symbol, the strange symbol? It looks a bit like a delta that is turned around, and that's a symbol. It is not so often used in normal mathematics, but it is really often used in fluid dynamics. And maybe if you know some open source CFD codes like OpenForm uses this symbol as a logo for its company. So this Nabla is really great help, great mathematical help, and it was named after music instruments in a really old picture. I placed it here upwards on the right side. This is a famous picture from the city of Ur, about 4,500 years old. Ur was placed near Baghdad in this region, and it was a really high culture in this time. It's even still a high culture. Okay, but they did a lot of science and a lot of music, and they invented a lot of things, and they used this Nabla instruments, and they really looked like this turnaround delta. What does this mean? It means if you have here, maybe go back a bit, if you here have, for example, this Nabla P, you make a derivation of this pressure in every direction of your control volume. So if you have, for example, here a coordinate system, you have a volume inside, phi, any variable, and you make a Nabla, or we also call it, you make the gradient of this symbol. It's like a derivation of your variable in every direction of your coordinate system. And what is cool at Nabla, if you have, for example, Cartesian coordinates with 3 coordinates, x, y, z, and you use this Nabla symbol, everyone knows in which direction you have to make the derivation, x, y, z. But if you have another system, like cylindrical coordinate systems, for example, or spherical polar coordinate systems, Nabla is also true. Yeah? It describes, for example, if you have a cylindrical system, it can describe the derivation into radial direction. So usage of this Nabla is really saves a lot of time for fluid dynamics specialists. Okay, so for example, we come later to the Navier-Stokes equations. You can write them really easy with the Nabla symbol. Okay, I've explained a lot, but I want to explain it more in detail. Here you have a fluid element. It's like a box that is a Cartesian coordinate system. You can have other coordinate systems, but we speak now about Cartesian coordinate system that was invented by Mr. Descartes or described by him. And if you have, for example, a pressure inside this fluid element, and now you want to calculate the pressure on the walls here of this aquarium. For example, this is an aquarium. Yeah? You have water inside, you have your pressure, and now we want to calculate how high is the pressure on every wall. Yeah? Then you can make the derivation into every direction. Here you can make, for example, if the aquarium is delta x long, let's say 1 meter, yeah? And if you have a pressure value here, you make a derivation over this delta x 1 meter, and then you get the pressure on the other side here. Or if you want to make a derivation on the bottom, you have to know how high it is, and then you make your pressure derivation, and then you can calculate it. Um, Also, I noticed during the exams that some of you students have sometimes problems with geometric calculations. Yeah, please also have a look how I always make some exercises about, for example, aquariums or houses or so. If you have to calculate this wall, how can you do it? Calculate it with the height times delta y. Or if you want to calculate the volume, how can you calculate it? Length, width, height, multiply it, then you get your volume. Okay, please always keep it in mind, this easy geometrical calculations, and make a note on your formula sheet and learn it, please. Okay, so we come back to the pressure on the wall. Okay, pressure calculations on the wall. And you can imagine, if you have an aquarium, if you want to build your water tank here and the pressure is too high, the glass will break because the stresses inside the glass could be too high. Okay, then the fishes can come outside. That's something that should not happen. Okay, so let's come back to the forces in the vessels. Remember, we don't have an aquarium, we have a more complicated object. Yeah, we have, for example, here one vessel on the left side and one vessel on the other side, and both are connected with a pipe. Yeah, this can be, yeah, for example, if we have here our aquarium on the left and we have a pump system on the right, and they're connected by a small pipe. What will happen with the pressures? We have here a pressure. Now we have here atmospheric pressure at the top. It would probably be 1 bar if we are on Earth. Yeah, maybe that's also a topic you should imagine. If we come, all these laws are made for the Earth, but if we come to another planet, maybe to Mars, we would need other gravity constants and other atmospheric pressures. Yeah? But here we're still on Earth. We have an atmospheric pressure here. We have a height of our vessel, and then we can calculate the pressure here on the left, on the bottom of our aquarium, and it is gravity constant times height times density of the fluid 1. And now we look on the right, maybe our pump system or so, and here it is the same. We will have a height set to a pressure at the bottom based on density and height and atmospheric pressure. And now if both vessels are connected with this pipe, we will always have a balance. Yeah? The forces on the left should always be the same as the forces at the right, because we want to have a resting fluid. There should be no movement. What happens if the balance is not fulfilled and we have different forces and different pressures? What happens? We will have a flow. But up to now we don't want to have fluid flows. Okay, here's an example where this system is used. It is, for example, used in hydraulic, when you deal with hydraulics. Yeah? Hydraulic pressures, hydraulic press, and they use the principle of this hydrodynamic different pressures. Yeah? Let's have a short look how this hydraulic press works. We have two vessels, they're connected, and here now they are not open. We don't have position of atmospheric pressure. They are not connected to the atmosphere, but we have here a piston. We have a force on the piston, and now, of course, we have the pressure of height. Here we have to multiply Z times gravity constant times density to get the pressure on the bottom, but we have to add also here the force divided by the area of this piston to get additional pressure forces. And now if we have one vessel that is really big, it has a high area, and we have one vessel that is quite small, smaller diameter and a smaller area, then we can get really high forces. Maybe you want to lift up a car, you need high forces. How can you do it? You have small forces here and high areas, and then you get high forces here and we have a smaller area. Okay, there's also this balance, and please always remember this force balance. You will need it if you want to calculate hydraulic problems or hydraulic presses or something like this. Okay, then there is another principle I want to mention, and that's also an effect of hydrostatics. We still have no movement of the fluid, but this is a principle it has to mention. Normally it's logical, but many people, if I would ask you, people would tell me wrong solutions. And this is the so-called hydrostatic paradoxon. The hydrostatic paradoxon, what is it? If you have vessels that look different, if you have, for example, this aquarium looks like an aquarium, or if you have like a bottle, it has the same, here it has the same area as an aquarium, but here on the top it's a little bit smaller. Or if you have a pot of water or something like this that gets higher, or even if you have an object looking like this, we always will have the same pressures in the same deep. It does not depend if we have how it looks like. It can be really small, and that's something unusual. Normally, if you say we have this object here, there's a lot of water inside, and if you have to carry it, you would say this is heavy. And if we have an object like this that is really tall here, or like this that is really tall, we don't have so much water, and we think we must carry it, we would say it is not so heavy. That is true, but the pressure inside will always be the same, because the pressure only depends on the height. It does not matter how thick the pipe is. And that's an effect you can also use it to prove the pressure inside big power plant vessel systems. If you want to look how many pressure you can fill into a big tank of a power plant or so, you just make a small pipe, fill it with water, and then you will get really high pressures inside the pipe systems. Even if you don't have a lot of water, that's a fact you can use. Or if you imagine you're a diver. You're a diver, a scuba diver in the sea. You want to dive down into the sea, and if you dive deeper and deeper, pressure gets higher and higher, and you should not dive too deep, otherwise you will faint or you can't breathe anymore. And it does not help if you dive into a cave under sea, or if you dive under a rock. You will everywhere have the same pressure. Even if you dive into a cave system, you will have really high pressures, even if you don't have a lot of water over you. That's a bit unusual, and so this effect is called a paradoxon. Okay, and we will also have some exercises on this hydrostatic paradox. Okay, here again, it's the same picture, same explanations. It does not matter how your tank or vessel look, if it looks like an aquarium or like a bottle or like like a dam system or a river, you will always have same pressures on the bottom. And I told you how can we calculate the forces at the bottom here. We calculate forces if we multiply the pressure with the area. And so if the area here on the bottom is the same, we will have same forces here. Even if these vessels don't have the same weight, which seems to be a bit unlogical. Okay, so because it's unlogical, we call it a paradox. Here again, just two other vessels. If we have different areas on the ground, we will get different forces. And if we now place these vessels on scales, we will get different, and if we only measure forces with the scales, we will get different results. And if I push my finger inside, if I have this glass, I showed you this glass in the first lecture. If I have water here inside, if I put my finger inside, we will get a higher level of this water, and so we will get higher forces. That's also something, maybe you must try it on your own with some scales and glass at home, and then you can believe me. Okay, let's look on the forces. We have this forces, and I showed you also here some dam system, for example, or I explained you something about a water dam. Maybe I have to put some picture of a dam inside later. And you can imagine if you want now calculate forces on a wall that has an angle, then it would not be so easy, this calculation, but you're all specialists in sinus and cosinus and trigonometry, and now you know what follows next. You can use the cosinus to calculate my area, and you multiply the area with the cosinus and the deep, and then you get the result. Okay. Here again, that's also an example I placed you here in the slides. If you have, for example, a big tank system filled with water, and you have a manhole here, a small door, because maybe it's a water tower, it's a really big tank, and from time to time you want to let the water, you want to empty your tank, and then you want to go inside to repair something, or imagine you have an undersea boat, then you have these doors, these manholes, and you must build this manhole. They should be waterproof, they should not get any holes or any damages, and so you must design your manholes. And the good question is now, how big will be the forces in the manholes? If we have here a wall which shifted in an angle, how can we calculate forces on these manholes? Because we want to prevent that when we fill it up with water, all the water will swallow outside. Okay, and that's also an interesting problem, and that's something I want to explain you also. You have to make here a solution for such manholes. I prove you the calculation is not so easy, but we will make it together in the next exercise. Okay, here again, same picture, forces on vessels. What happens if, I explained what happens if we have manholes or if the walls are a bit shifted. And another thing that could happen is that the walls are round, like a pond. Then we will have the same laws. we have pressure times area is the force. Yeah? We can use always the same law. Here we have a pressure inside the pond. You can calculate it by the deep. It will be deep will be the only driver to rise the pressure here, but you can imagine the area, the calculation of the area is yet now quite tough and difficult. Yeah? If you have a normal rectangular aquarium, it's easy to calculate the area. But if we have an object like this that is round, we have to make an integration, for example here of a ball, yeah? And integration of a small element of a small region, and this will be not so easy to calculate this area, but doesn't matter. If you have an area, if you multiply it with the pressure, you get the forces on every element. And if the object, for example the river or the pond, is more complicated, you have to make a lot of small, you have to calculate a lot of small areas. It's not really difficult, but it's time consuming. And I can explain you, I had once an industrial project about fluid flow problems in the Rhine River, and they even sent me a really detailed map of the ground of the Rhine River, and I had to calculate a lot of small elements here on the river, on the ground, and then it was possible to calculate forces. So, or here, how does this look like? We have here a river, for example, and we have complicated geometrical, and so we have to calculate for every region, for every different region, small delta areas, small area elements, yeah, and then we can calculate the forces. And that's something. Why do I explain this to you? You can imagine nowadays it's really tough and difficult to calculate all the small areas, but that's where we will use under CFX. Under CFX we can divide all the areas in small sectors and make the calculation.